Hello everyone, welcome to our channel. This is Dinesh MA, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. In today's session, we'll understand field effect transistors. Field effect transistors, which are called in short as FETs, or voltage operated devices that are used in amplification and switching applications. FETs have got a huge input resistance, which is considered to be an advantage over the bipolar junction transistors. And these FETs are classified mainly into two types. Number one is called as junction FETs or junction field effect transistors. Number two is MOS FETs or MOS field effect transistors. Further, these are subdivided into two types. One is called as N type and the other one is called as P type. First we'll understand the junction field effect transistors and then we'll understand the MOSFETs or MOS field effect transistors. So we'll be understanding the fabrication or the construction of FETs and the working of FETs and the VI characteristics of the FET. Now let us understand the construction or the fabrication of N-channel JFET. So this is construction of JFET. So as the first thing, we'll consider a layer of P-type substrate. So this is going to work as the substrate. Now into this substrate, P-type substrate, will diffuse an N-type layer . So this is N-type material that is going to work as channel, and then into this N-type layer will diffuse the P-type impurities that looks like this. This is P-type material. Now these two P-type material will be working as gate regions, whereas this N-type material will be working as channel, and these two ends of the N-type channel will be working as source and drain terminals. Now to facilitate the terminals over this, what we'll do is upon the surface of this we'll deposit a layer of silicon dioxide. So this is made up of SiO2, and now finally we'll deposit the metal layers. So these are the metal layers through holes what we have created, and here we can see this is the metal connected to this P-type material and this is connected to this P-type material. So these two will be working as gate terminals, whereas this which is connected to one end of the N-type channel and this metal layer which is connected to another end of the metal layer, this will be working as source, whereas this will be working as drain terminal. So this is the cross-sectional view of an N-type JFET. Because the channel is of the type En, this will be called as N-type JFET. If in case the channel is made up of P-type, then JFET will be called as P-type JFET. Now, the symbol of N-type JFET can be written like this. So, this terminal indicates gate, this is source and this is drain. So, this is one of the ways how we write the symbol of N-type JFET. Now, this can also be written like this. So, this is gate terminal, this is source terminal and this is drain terminal. Now, here we understood that there are two gate terminals, but in the symbol we have only one gate terminal. Now, we can indicate the other gate terminal also. So, the symbol then should be written like this. If this is gate 1, this will be written here. If this is gate 1, gate 2 will be written like this. This will be source and this will be drain. So, this is the cross-sectional view or the fabrication of the N-type JFET, and these are the symbol representation of N-type JFET. Now, we will understand the working of this JFET. Now, let us understand the operation of N-channel JFET. To understand the operation, we will be considering three conditions. Number one is with VGS equals to 0, with VGS equals to a small negative VGS and with a large negative VGS. So, these are the three conditions what we will be considering to understand the operation of an N-channel JFET. So, let us consider this diagram where we have the N-type channel. This is N-type channel and this is sandwiched between two P-type gates. So, these two are gate regions and this is the channel region, and let us say this is drain terminal and this is source terminal. So, to understand the operation, what we will do is we will apply a positive drain to source voltage. I mean to say a positive drain voltage with respect to source. So, let us consider source connected to ground potential, whereas VGS should be 0. So, the gate voltages or the gate terminals will be kept open. So, we are not connecting any voltage at the gate terminal. Now, with this condition, with VGS kept open or is equal to 0, what happens? Because of this positive drain voltage with respect to source, there will be an electric field induced in the channel region. And this electric field induced in the channel region will make the electrons to drift, the charge carriers move from the source region towards the drain region. And because the charge carriers are moving from source to drain, the effective current will be flowing like this from drain to source. So, we say there is an current IDS flowing in the device. As we vary VDS, the amount of drain to source current will also be varied. If we decrease VDS, IDS will be decreased. If we increase VDS, IDS will also be increased. So, this is how the N-channel JFET works with VGS equals to 0. Now considering a small negative VGS applied. So let us rewrite this diagram. This is N-type channel, and here we have P-type gate, here also we have P-type gate, and this is drain terminal where we have applied a positive VDS, and this is connected to ground potential. This is source terminal. So this is P, and this is N. And as we have considered here, what we'll do is, this is gate, so what we'll do here is, we'll apply a small negative VGS here also. So these two values are going to be same. So what we have done is, a small negative voltage has been applied at gate with respect to source. And here what we can see here is, this P-type gate, this P-type gate and this P-type gate forms a PN junction with this channel. So this forms a PN junction, this forms a PN junction. And because the P-type gate terminals have got negative voltage with respect to N-type source terminal, this makes this junction reverse biased. Right? So this makes this negative voltage at the gate with respect to source make these two PN junctions reverse biased. And because these two junctions are reverse biased, there will be depletion regions developed across the junction. And here the point to be noted is, the N-type channel is lightly doped compared to the P-type regions. Because the N-type channel is lightly doped, the depletion region towards the channel will be deeper compared to the gate regions. So what is this? This indicates the depletion region. Because the N channel is lightly doped compared to the P regions, so the depletion region penetrates deeper into the N channel region. Now because there is a depletion region penetrated in the N channel region, this will increase the resistance. The channel resistance will be increased. Because the channel resistance is increased, so this will pose a restriction on the movement of the charge carriers. So because of this, the IDS will be decreased. Right? So because the gate has got a negative voltage with respect to source, this has caused a reverse biased condition on the PN junctions, and because of this reverse bias condition, there is a depletion region developed across the junctions, and this depletion region is deeply penetrated towards the N channel region, and because of this the channel resistance has been increased. Because the channel resistance has been increased, the drain to source current has been reduced. Right? So this is the condition of the N channel JFET when we have connected or applied a small negative voltage at the gate with respect to source. Now we will further understand what happens if we further increase this. So if we further increase this negative voltage at the gate terminal, so how the device N channel JFET is going to behave. So that we'll understand. So let me write again the diagram of the N channel JFET. So this is N type, and here we have drain terminal where we have connected a positive drain to source voltage. So this is source terminal which is connected to ground potential, and here we have gate. This is secondary gate. This is gate. This is also gate. And here we have supply voltages connected. So what we'll do is, let us make gate more negative. Right? So this is VGS. Right? So here also we have more negative voltage connected at the gate terminal with respect to source. So because the, let me write these two as P type. So because the junctions are more reverse biased, we know the basics of a diode, the depletion region will be growing more or growing deeper. So because of this, see what is happening, the depletion region will grow much deeper and touch each other. The depletion region across this junction and the depletion region across this junction will grow much deeper and touch each other, and because of this what happens, so there would be the IDS, the drain to source current, which is going to be diminished. So because there is no way for the drain to source current to flow from the drain to source region, so IDS is going to be diminished here. So we can say IDS is going to be approximately 0 in this condition. So what we have, three different conditions we have here when there is no VGS. In all the three conditions what we have is a positive drain to source voltage we have considered. Now when VGS is equal to 0, when gates are kept open, there is no restrictions for the charge carriers to move around in the channel region. So as we vary the drain to source voltage, so accordingly the IDS, that is drain to source current, will be varying. As I indicated, if I decrease VDS, IDS will be decreased. If I increase VDS, IDS will be increased. So more the VDS we supply, more the electric field induced in the channel, more the electric field induced, more the charge carriers will drift, more the velocity, more the current flowing in the channel. And when we have connected a small negative voltage at the gate terminal with respect to source, so there will be restriction because of the reverse bias junctions, and because of this there will be depletion regions penetrated into the channel region, and this poses higher resistance levels in the channel. Because the channel resistance is increased, the drain to source current will be decreased. However, VDS will be having control over IDS still. So again, by varying VDS we can control the amount of the current that is flowing, but there is a cap given for the IDS, for the higher level of the IDS. And further, if I increase the negative voltage at the gate terminal, the depletion region in the channel region will grow deeper and touch each other, and this will cause a huge resistance in the channel. So channel resistance is going to be high, and we know when the resistance is high, the current is going to be almost 0 or less. So under this condition, IDS is going to be almost 0. So this is the operation of N-channel JFET. Now we will understand the operation of P-channel JFET. Let us consider P-type JFET. And P-type JFET looks like this. So this P-type JFET will be having the channel that is made up of P-type material, and this P channel will be sandwiched between two N-type layers. And these two N-type layers will form the gate region. And here we have the drain terminal, and here we have the source terminal. So now to understand the operation of this, what we'll do is, because the channel is p-type and holes are the majority charge carriers, the drain need to be connected to negative VDS. So drain will be having negative voltage connected with respect to source. So let the source be connected to ground potential. So now because of this, the charge carriers that are there in the channel region will move around and there will be a current flowing in the device, and drain current will flow out of the drain terminal. So this is going to be a negative current. Now to understand the effect of the gate terminals or the gate to source voltage on the IDS, what we'll do is, the PN junctions, let us make these two reverse bias. So in order to make these two junctions reverse bias, the gate terminals need to connect it to positive gate to source voltage. So let us say we have a positive gate to source voltage connected here to the same plus minus, this is VGS, and this is also plus minus, this is VGS. So these two positive voltages will make these two junctions reverse biased, and because these two are reverse biased, we have the depletion regions penetrated. So more it will be penetrated towards the the channel region. More the VGS becomes positive, more the depth of the depletion regions into the channel region, and more it becomes deeper, more the channel resistance will be. So higher the positive voltages, the higher the channel resistance becomes. So more the or higher the channel resistance is, lesser the IDS will be. So when we increase or when we make VGS more positive, it will increase the channel resistance, in turn that decreases the drain to source current. So this is the operation of p-type JFET, and the symbol of p-type JFET will be written like this. This looks similar to the symbol of the n-type JFET except for this arrow mark. So this indicates the gate terminal, this is drain, this is source terminal. So there is another way to indicate the symbol or write the symbol, that is just the position of the gate terminal will be shifted high, if not everything remains same. So these two are the symbols of the p-type JFET. So this is all about the operation and symbols of p-type JFET. Now let us understand the drain characteristics of JFET, and we'll consider n-channel JFET for the discussion. So let us get into this. So we'll understand drain characteristics of n-channel JFET. Now we'll consider two conditions. One is with VGS equals to 0, the other one is with some external voltage applied between gate and source terminal. Now with VGS equals to 0, to understand or to draw the drain characteristics, so what we need to do is we need to consider an n-channel JFET with VGS equals to 0. So let us draw the circuit diagram for this, and this is the JFET what we have. So this is gate terminal, this is drain terminal, and this is source terminal. Let us consider here, this is ammeter which measures the drain current and apply a drain voltage VDD, let us say VDD, and then we'll measure the voltage between the drain to source voltage. So this is voltmeter which is going to measure as VDS, and say this is equal to 0. I mean the voltage between gate and source voltage is equal to 0, and let us say this source terminal is connected to ground potential. So this is a circuit diagram what we have considered to understand the drain characteristics. So what we'll do here is we'll understand how the VDS, how the IDS varies according to VDS. So let us plot the drain characteristics where we'll consider the ID versus VD or IDS versus VDS plot. So let us say this is origin, and on x-axis we'll consider VDS which is measured in volt, and on y-axis we'll have IDS measured in milliamperes, and let us consider the step size to be 2 volts on x-axis and even on y-axis we will consider a step size of 2 milliamperes. Right. So now to understand the drain characteristics with VGS equals to 0, so what we'll do here is, now with VDS equals to 0, what we can see is there would be no IDS flowing. So with the operation we have understood that if VDS is made 0, then there would be no charge carriers, there would be no field induced in the device. So no field is no charge carriers will be moving, no charge carriers moving, there would be no current. So if VDS is made 0, then IDS will also be 0. So for VDS equals to 0, IDS equals to 0 we have. Now further, if I increase this VDS by a small amount, let us say less than 1 volt, then there will be a small increase in the IDS value. So IDS, a small IDS will be flowing in the device that causes or that generates a voltage drop across the channel, and this voltage drop across the channel will have a depletion penetration done in the channel, but this has no effect on the channel resistance. Further increase in VDS, will have a linear, approximately linear increase of IDS. So the characteristics looks like this. So further increasing on VDS will have a linear increase on the output current or IDS. Now if I move further on VDS beyond 2 volts, it will have lesser or smaller increments in IDS. So it looks like this. A smaller increments will be having. So it looks like this. So further increase on the VDS will have more penetration of the depletion in the channel, and this causes almost no control of VDS on IDS. So IDS almost looks like this. So it becomes almost equal to 0. So the point at which the IDS becomes saturated, the current will be called as IDSS, that is saturated, the saturated drain to source current, and the point from VDS equals to 0 and IDS becomes IDSS, this region will call as channel ohmic region, because the device will be working as a resistive element. As I increase VDS, IDS also increases linearly. So this region will be called as channel ohmic region, or this can also be called as linear region. Now the point at which the IDS becomes almost constant, this voltage will call as VP. This voltage will call as VP, which means pinch off voltage. So the voltage at which the current becomes almost constant, the voltage point will be called as pinch off voltage, and the device is said to be pinched off. Now further, if I go on increasing the VDS, this will cause the device to break down, and the point at which the device gets break down, say for example here, if I go further on beyond this, the device gets break down and there will be a sudden increase in the current, and the device is said to be in the breakdown region. So the voltage at which the breakdown occurs, so this point or this voltage will be called as breakdown voltage. So this voltage will be called as breakdown voltage, and this region is called as breakdown region. So this is ohmic region, and this is breakdown region, and this is the pinch off condition or the pinch off region. So this is the VI characteristics of the N channel JFET, or drain characteristics of the N channel JFET for VGS is equal to 0. Now we need to consider another condition. What if this VGS is changed? We have understood in the operation, right? So when VGS is equal to 0, there would be no depletion region formed because of the reverse bias condition. No reverse bias condition occurs, so there is no depletion region penetration occurs. Because there is no depletion region occurs, ID will be flowing easily. Now if we apply some negative gate to source voltage, this causes the PN junction to be reverse biased, and because of this there will be deeper penetration of the depletion region into the channel, and this causes reduced IDS. So this is what happens when I change the VGS level. So let us consider here, we have a negative VGS. We have applied a negative VGS. So because of this negative VGS, as I just mentioned, the ID levels will be reduced. So here this is, let us say, VGS is equal to 0. So if I decrease, if I make VGS equals to some negative value, then this may look like this. So again there will be further increase, there will be a linear increase, and the saturation will be occurring at a earlier value of VDS. So saturation or the pinch off may occur before 4 volts as compared with VGS equals to 0. When VGS was equal to 0, the pinch off voltage was occurring after 4 volts. Now this is just an approximation what we are using. If VGS is made minus 2 volts. For example, the pinch off will occur. The IDS value varies and the pinch off value also varies. The pinch off condition will occur at the earlier stage. So this will be the Vp for VGS equals to minus 2 volts. Right. Further, if I decrease the VGS value, then let us say this is for VGS equals to minus 4 volts. So again here what you can see is this is Vp for VGS equals to minus 4 volts. So in the drain characteristics, what we are understanding is if I make VGS equals to 0, I'll have higher levels of IDS. If I make VGS negative and more negative, the IDS values will be reduced, and even here the breakdown levels will also be occurring at earlier values. So this indicates the breakdown regions. So this is all about the drain characteristics of N-channel JFET. So here we have considered two conditions. One is when VGS equals to 0, another condition is when VGS is equal to some negative voltage. Let us understand the transfer characteristics of the JFET, N-channel JFET. And the transfer characteristics is how the ID varies with respect to changes in the input voltage. So the input voltage is VGS, output current is ID. So this is the transfer characteristic, this is the drain characteristics what we have. Now the transfer characteristics is because the input voltage VGS is negative, so we will consider the extended x-axis in the reverse direction. So let us say this is 0.1, 0.2, 0.3, 0.4, sorry, minus 1, minus 2, minus 3, minus 4 and minus 5. So let this be VGS in volts, because here we have considered in steps of minus 1, minus 2, minus 3. So here the analysis what we did with minus 2, minus 4, let us say this is minus 1 volt and this is minus 2 volts. Right, so further if I go on decreasing the VGS, so the ID levels will be decreased as I just explained. Just I have changed the references what I have considered. Now as I just indicated, transfer characteristics are the plot of IDS versus VGS, how IDS varies with respect to VGS. So now this plot, the transfer characteristics plot is the region occupied by ID is equal to IDSS and VDS equals to 0 and ID is equal to 0 and VGS equals to VGS off. So this is nothing but, here you can see this is the IDS level for VGS equals to 0, right. Now if VGS is reduced to minus 1 volt, IDS level is reduced. So what we have is, so this is for VGS equals to 0. Likewise, if VGS is decreased to minus 1 volt, if VGS is decreased to minus 1 volt, so here the saturation level will be 8 milliamperes. Likewise, if VGS is decreased to minus 2 volts, if VGS is decreased to minus 2 volts, IDS is 6 volts, so it will be having somewhere like this. Likewise, if VGS is further increased to minus 3 volts, IDS may be 4 milliamperes. So here this may be somewhere like this. And further if I decrease VGS level to minus 4 volts, it may come over to this particular point. If I further decrease VGS level, it may settle somewhere here. So the transfer characteristics looks like this. Let me join these points. somewhere the ID becomes 0, and this is the point where I call VGS equals to VGS off. So where ID becomes 0. So this is the transfer characteristics of the N-channel JFET. So this shows how ID varies with the VGS variations. So as I go on varying VGS in the negative direction, what I can understand here is the IDS values have been reduced. This is what we understood when we discussed the operation of N-channel JFET, right? So you remember that? So when we increase the VGS to more negative levels, more depletion regions penetration will be there, and that increases the channel resistance, which in turn reduces the IDS values. That is what we are witnessing with the transfer characteristics also. As we make VGS more negative, the IDS value will be decreased. So this is the transfer characteristics of the N-channel JFET.